we're going to cover pipelining. That's an exciting topic too. All processors today are pretty much pipelined. And actually many of them are out of order execution. So we'll go into those topics. But before, we need to finish the microprogrammed microarchitectures, which you're hopefully having fun with in your homework. If not, you will be having fun with it. But remember that it's due next Monday. Oh, it's faster than I thought it would be due. It is due next Monday, right?
At least it's not this Monday.
No, this Monday is today. It's not due today. But you'll have labs and homeworks due in a staggered way every other week. So it's going to be a fast-paced course, but hopefully you'll have fun with it. Microcode. This is going to be probably the most time-consuming part of the homework, writing the LC3B microcode. But you'll learn a lot, I promise. You'll use that in the future. And, you'll have fun with the other questions too. And lab assignment 2 is due February 15th, which is next Friday. So as I told you when we started the course, it's going to be a fast-moving course. So you should definitely keep pace. And definitely let us know if you're not keeping pace so that we can help you in some way. Justin and Yungu and Jason, who are not here for some reason, but they will be. They can help you in the lab sessions, as well as recitation sessions, as well as through extra office hours. And yeah. And you know what Lab 2 is about, right? It's a first Verilog assignment, single cycle MIPS implementation. Should be fun. And there's extra credit too. And I already talked to you about this, but we have assigned some fraction of your grade. It's actually a lot of extra credit. So if you complete the microcoded MIPS design for Lab 2, you'll get 4% additional of the course grade. So if your course grade in the end is 88, and I know you're not here for grades, but if your course grade in the end is 88%, it'll go up to 92% if you've done the full MIPS design. So hopefully this will give you some incentive to actually try to do at least part of the microprogram design. And you will get extra credit even if you do not complete the full design. So I'd like to emphasize that. If you attempt some things, and if those things work, then we'll give you extra credit. But you should demonstrate it well to us. Okay? That's a place where you can exercise your creativity. So hopefully you've done the readings for today, and the lecture will go nicely, and you'll ask some questions about pipelining. And I have actually added this optional reading from the Hammaker Zaki Varnesic book on computer organization, right? And chapter 6 talks about pipelining. It's a more higher level overview, but it gives you the basic concepts. Whereas this Patterson and Hennessy chapter is more implementation-oriented view of how you actually design a pipeline. Okay, today that's what we will do. Finish microprogram microarchitectures first. I'll very, very quickly remind you what we've done. We've done a lot last lecture. We did an exercise in microprogramming. We went through how many states? 4? Or was it 5? 4 states, maybe, you're right. That's right, yeah. Yeah, there are 3 stages in fetch, remember, in the LC3B, and then 1 decode stage, and we've done all those stages. And you're going to do the rest. And I think actually it's 5 because 2 states are the same, right? States 18 and 19 are the same. But that's a freebie. Okay, so this is what we've done. This is just to get you started as review material. We've covered this. You're going to implement. You're going to actually deal with this for the rest of the course for a while. We're going to pipeline this design at some point, maybe in the next lecture. And we've covered these states. This is just to show you one particular instruction for load word. I'm not going to cover the rest of the states because now you got the gist of it. You can do it on your own. Okay, this is what we had in the slides. So basically, you're going to fill out this one for your homework. How many of you are done with it? Oh, we have 2 people. Excellent. Does it work? You think so? How do you verify it? Maybe you should actually do the design. But that's good. I'm glad you guys are moving ahead quickly. OK, and that's a microsequencer. This actually, I think of this as a beautiful design because it's very well thought out. Think about, this is the design you're given, right? You're not designing the microsequencer for your homework, but for your next homework, we will actually ask you to add instructions to the LC3B. And I'll tell you what instruction that is. And change all parts of the microprogram control to support that particular instruction. And there may be exam questions. If you look at past exams, we've asked questions like, here are the modifications we made to the data path, and here's what happens. What does this instruction do? Or the other way around also. You could reverse engineer what the instruction does based on the state machine, new states added. Or we could give you an instruction and ask you to design the additional states, additional changes to the microsequencer, additional changes to the data path to actually make that instruction work, fit within the microprogram design. So hopefully you should be able to do that after you do all this homework. But it's fun. It's what happens in a real machine also, actually. If people want to add more instructions, for example, to an Intel machine, especially if it's a complex instruction, what they can do is they can translate it to different micro instructions, and they can add new micro instructions. And they do add new micro instructions to the Microcode store. And that's how they support new instructions. That's a very easy way of supporting new instructions. So what you will be doing is a mini version of what people are doing in real life today. OK. Some questions on the microsequencer. I think I'll go through this quickly. Actually, we've covered this. What happens if an illegal instruction is decoded? I don't think that we've covered that one. Any ideas? First of all, is there an illegal instruction in LC3B?
There's not.
Say it again?
There are two instructions we don't define the behavior of in the subset we're implementing that I believe you said were used for interrupts. And currently those are implemented as a jump back to the start state.
That's right, yes, exactly. You're not implementing those. So currently those are implemented that way. So which means that they're not illegal, right? They're legal, but you're not implementing them in your design. But there are a couple of instructions that are not. Oh, there you go. There's my instruction set. And somehow we need to fix the software. Maybe it's going into a service routine that just doesn't bring in the doccam, right? Anyway, so if you look at this, anybody can see, there are two instructions here, 1010 opcode and 1011. They're not used, right? What if the program contains that instruction? Then what happens is you can actually go into a state. You can actually add states into the state machine. Even though I don't have the doccam, I can use this one. Are these instructions? 1011. There you go. To 11. So these states, these are illegal instructions. They're undefined instructions. So these states could be exception handling states, right? You could actually add states here that handle an exception somehow, that save the state of the machine, and then jump to a user level or system level service routine that somehow displays to the user, you've executed an illegal instruction, right? So you could actually have a state here. We're not going to implement it in our labs, but we could do that. That handles the exceptions. So your entire machine is essentially based on this finite state machine, right? So you could handle all kinds of exceptions also in your design. That's one of the beauties of microprogram machines. OK, how is variable latency memory handled? You know this very well by now, right? Basically, you have this arbit, right? Arbit says memory is ready or not, and based on that, the next state is conditional on that. And how do you do the state encoding? I'm not going to go into this, but this is actually kind of an art also, art and science together. you would like to minimize the number of state variables, right? And this has been a problem in especially early machines when hardware cost was very important. You could not put a lot of memory. Because if you think about the control store, it's memory, right? It's memory that's specialized memory that's implemented on chip. And you would like to minimize the size of that. To be able to minimize that, you would like to minimize the number of states, number of micro-instructions. Then the question is, how do you actually minimize the state variables? Right? And your encoding of the states now matters. Well, in this case, there is a big state that kind of determines the encoding, obviously, right? Because you're doing a multi-way branch to 16 different states. So you can start with the 16-way branch and assign the state numbers to those next states, and then determine somehow the constraint tables, which you've seen in 240, hopefully, and states that are dependent on these conditional bits, and based on that, do the state assignment. Okay. This is actually 240 material, so you can think of that way. But when you're designing a microcode machine, you need to do this also, especially if you want to minimize the control store, as well as the microsequencer latency, right? State encoding also determines the latency through your control logic. Because one thing you could do is perhaps you could have a kind of a stupid design in which you can do if, else, if, else. If my state is this, do that. And based on that, you could do a hardwired logic implementation of a microsequencer without worrying about how those states are dependent on the conditions, right? Basically, the microsequencer is designed such that the condition that changes two states, the state variables are assigned such that states dependent on the same condition are far apart from each other in terms of the control store entry location based on that bit that determines that distance, right? I didn't explain that too well, but you get the idea, right? For example, if we go back to the microsequencer, yeah. States that are dependent on this ready bit are far apart from each other by 2 entries in the control store, because only the second bit determines whether your state is memory ready or memory not ready, based on that. But you didn't, if you didn't do your encoding well, those states may not have been far apart from each other only by 2 entries, right? They could be anywhere in the control store. Now that changes your microsequencer, and that also increases the size of your control store potentially. Okay? Well, maybe it doesn't increase your control store, but it makes your microsequencer much more complicated right now. And this could become your critical path if you do not do that encoding well. Okay? So all of the decisions that you make affect your critical path. Yes?
Do you have a closed aimings? So
these two?
Yeah. So yeah. Change by 1 bit. It says they are far apart numerically, but the training distances are.
That's right. But that's because the microsequencer is designed this way, right? Your state variables are assigned this way. But you could have said, if you could have said, if the memory is ready, the state is 10. If the memory is not ready, the state is, I don't know, 31. There's no way you can design a microsequencer that's conditional this way. Then it becomes an if-else statement, and your microsequencer becomes long latency. Right? So think about, we've given you this design, but this design is actually based on design decisions to minimize this latency through the microsequencer and minimize the number of states. Okay. Okay, another question. What control signals can be stored in the control store versus what control signals have to be generated in hardware logic? You see both here, right? And we've discussed this briefly in the last lecture. Some control signals actually have to be generated in a hardwired manner. Anybody remember what those are? Yes? SR2 mux. That's true, yeah. That's that control signal generated by the hardware. Yes?
There were a bunch of like the memory.
That's right, yeah. There is a distinction between those two, actually. SR2 mux, maybe you could store it in the control store if you make your control store wider and index it with different things, potentially. But memory may be harder, right? Because if you look at well, I guess another way of putting this question, what signal cannot be available without processing in the data path? SR2 mux is part of it, because that that requires decoding part of the instruction. But if you actually use that decoded part of the instruction to index into your control store somehow, maybe you could generate SR2 mux through your control store, and I'll let you guys think about that. But in terms of memory, it may be harder, right? Because your address is generated. Now this is where we need the dock camera, maybe, or maybe let's go back to this. Okay, I don't know if you guys can see that memory, but you have your handout, hopefully. So if you look here, there is this additional control logic that takes memory address and decides control signals for these muxes, right? And this additional control logic decides whether memory should be enabled or I/O should be enabled, and which I/O register should be enabled. And that's dependent on the address, right? This is memory mapped I/O. This is very, very hard to generate using the control store, right? How do you do that? Well, you need to have the memory address available. Maybe you can design a control store that's based on the memory address, right? But that's going to be a different control store now. So that's very tough to do. That's why you need hardwired logic also in addition to the control store. These are not exclusive ways of implementing control. Okay, so I'll let you think about that a little bit more also. Okay, variable latency memory. We've already talked about this. So can we handle this in a single cycle microarchitecture? No, right? It's single cycles. You have to wait for the worst case. There are other questions also. What happens if the machine is interrupted? You could actually add states that check for this interrupt condition, right? And this is not in the state machine, but for example, you get an interrupt from a device, let's say keyboard, that gets registered from the device into a register in the processor. An interrupt bit is set. You could have a state that checks that interrupt bit and jumps to some other state, right? You could actually do it in every possible state. You could check the interrupt. But we will see that we would like to have precise exceptions, right? We'd like to handle the interrupt at a clean place when all of the previous instructions are finished and when no later instructions started. So it makes sense, perhaps, to check for an interrupt. I keep going back. This is where technology would have helped. It makes sense, perhaps, to check for that interrupt right here, right, in this state, before fetching the next instruction. Or maybe, well, maybe in all of these states. Although it's probably better to have a single place where you check the interrupts, right? Another option is to add another state that just checks interrupts. Good idea? Bad idea? The suggestion is, instead of jumping to 18, 19, have another state you jump to, and the sole purpose of that state is checking for interrupts.
Might be a better idea.
Better idea.
So
Why?
don't burden down the one state that has to check a lot of things. You can keep your cycle periods short.
That's true if what you're checking is dependent on any of these, right? In this case, the interrupt bit is independently set.
But wouldn't you need to check the interrupt bit before deciding where to put your PC on?
Yes, so you need to handle that well. Yes?
If you keep it separate, you know you're adding a cycle.
Mhm.
But if you don't, then as long as it's not increasing like the maximum latency of all the states, then you can just put it in the same instruction or the same micro.
That's right, yes. So that's a good answer, actually. So if you have another state just for checking interrupts, then every time you have to go through that state. You're basically adding a cycle to every single instruction. You're increasing cycles per instruction, right? Whereas if you're putting that check into this state, you may be increasing your cycle time. But in this case, the interrupt check should not be increasing your cycle time, hopefully, right? Or you can design the logic such that it doesn't increase your cycle time. So adding that extra state just to check interrupts is actually a bad idea, because you should be able to design the machine such that that interrupt check is not on the critical path. Okay? Maybe we should have a lab where you actually do this so that you'll have fun with the interrupt handling. Okay, so the fundamental trade-off is, again, always there, right? The equation, remember? This is your execution. Well, I don't want to go over what's written here. Okay. Your execution time is number of instructions times cycles per instruction times cycle time. If you're increasing this always without changing the cycle time, you're basically increasing your execution time. That's what's happening if you add one more state. If you don't add one more state, you're not increasing this. You're doing things concurrently there, but you may be increasing your cycle time. But as long as you make sure that your design is such that you're not increasing your cycle time, that's a better idea, much better idea. Okay, and in general, interrupt and exception check logic should not be in your critical path. You should not design a machine where interrupt and exception checking or handling is on the critical path. Okay, that's a bad design. And if you see such a design, you can fix it probably. Okay. Oh, okay. Another question is, how can you implement a complex instruction using this control structure? For example, repeat MOVES, right? We go back to repeat MOVES that you did in your homework 1. That's a fun instruction. You could actually implement repeat MOVES as a sequence of micro instructions, right? You could actually implement that as a sequence of instructions that are implemented as micro instructions. Think about that for a while. But basically, what I'm getting at is this microprogramming, the concept of this micro instruction is very powerful. It provides you an abstraction. It enables a hardware designer to program the underlying machine. Right? The designer can translate any desired operation into a sequence of micro instructions. And if the micro instruction if those primitives that do not if you do not have enough primitives to implement repeat MOVES, you can add another micro instruction as the hardware designer, right, to enable that much more complex instruction. Basically, all the designer needs to provide is the sequence of micro instructions needed to implement the desired operation, think repeat MOVES again, or multiply without having a multiplier, the ability for the control logic to correctly sequence through these micro instructions, so your micro sequencer should be correct, and any additional data path control signals needed for that particular operation. As long as you do provide these, then you can implement any complex operation using this very simple structure and program a very simple data path, make it do anything you want, pretty much. Okay, this is what you can read. So I think we'll do some more microprogramming, not right now, but this is for your homework 3. You'll implement repeat MOVES in the LC3B microarchitecture. You will need to do, I believe, all of these. Maybe not all of these. Maybe you don't really need additional data path control signals. But I haven't thought about this in a while. And I'd encourage you to try to minimize your design. Then the question is, what changes, if any, do you make to the state machine? Hopefully, you will need to make some changes to the state machine, the data path, the control store, and microsequencer. That sounds like fun, right? And you'll show all changes and micro instructions. So this is coming up in homework 3, not homework 2. Homework 2 is first microprogramming the existing machine. Here you're going to improve and make LC3B do repeat MOVES. And repeat MOVES will be one of those undefined instructions currently, right? It will be defined. You'll add those states. Okay. And this is actually how repeat MOVES is also implemented in an Intel machine today, right? You sequence through microcode and generate micro instructions, go through states. When a repeat MOVES instruction is fetched, the machine goes into a special mode. It transfers control into the micro-coded engine instead of doing the pipelining. And that microcode engine generates sequences through states and generates micro instructions and inserts them into the pipeline such that that repeat MOS executes correctly. And then at the end, when the repeat MOS is done, when the microcontroller figures out that the repeat MOS is done, then the machine goes to the next instruction. Yes?
Are the microcode normally stored in flash memory or hardwired?
So it has to be very tightly integrated to the pipeline. So it's actually hardwired in the processor itself.
So it would be possible to like grab an x86 and then do some random hacks and start modifying its micro sequencing.
Okay, so microcode updates, we'll get to that. If you have the right privilege level, you could potentially do that. But that needs to be privileged, right? Okay, we can get that, yes?
So strictly speaking, then your control store is not actually a memory, per se.
So your control store is not visible to the programmer.
Right.
So it's actually a memory structure, hardware memory structure, right? From a hardware point of view, it's memory, but it's not in your main memory.
Right.
It's in your processor.
But it is like an array of cells.
Exactly, it's an array of cells, basically. But it's fundamentally storage, right? You have to store some bits for micro instructions. But we will see there are many, many designs that actually either expose or not expose to the programmer. Today, what I've described to you is not exposed to the programmer, right? You cannot modify it as a programmer. As a hardware designer, you can modify it. Okay, alignment correction, we've talked about this. This is, remember, unaligned accesses. And actually, I've shown you the logic in the last lecture that does alignment of bytes in LC3B. So LC3B has byte load and byte store instructions that move data that are not aligned at the word address boundary. Do you put the byte, do you take the byte at the top part of the word or bottom part of the word? This provides convenience to the programmer, as we've discussed. How does the hardware ensure this works correctly? Well, if you look at state 29 for load byte and states 24 and 17 for store byte, you will see that. And I've described you some logic to do this. So you need some additional logic to handle unaligned accesses. So we won't go through this right now. And memory mapped I/O, we just discussed this, right? There's some address control logic that determines whether the specified addresses are to memory or I/O devices. And this logic correspondingly enables memory or I/O devices and sets up the muxes. And all of these are actually found in today's machines. LC3B is a little version of today's machines. Okay, we already discussed this. Okay, so let's start wrapping up the microprogram control. There are many advantages to this kind of control. First, as you've seen, it allows a very simple data path, a single bus data path, to do powerful computation, very complex instructions, repeat MOS, as you will see, by controlling the data path using a sequencer, right? Basically, high-level ISA is translated into microcode, sequence of micro-instructions, and microcode enables that minimal data path to emulate the ISA. And you can think of these micro-instructions as user-invisible ISA. But we will see that people have actually exposed this to the user in the next slide. Actually, if you've done one of the readings that I've suggested, the Burroughs 1700. Burroughs 1700 had a user-programmable microcode engine. So that microcode was part of the ISA, actually, which was interesting. Okay, it also enables easy extensibility of the ISA, as you will see in your homework 3. You can support a new instruction by changing the microcode. And you can support complex instructions as a sequence of simple micro-instructions. You could actually have a higher level sequencer that goes through your microcode sequencer. And we will see that also. Some people call this millicode. Also, basically, your microcode engine is called over and over by some higher level engine. And you can think of the levels of hierarchies of microcode, right? And I guess this is written in an interesting way, but if I can sequence an arbitrary instruction using the microcode, then I can sequence an arbitrary program, right, as a microprogram sequence. This is what I meant just now. You could have a higher level program. Basically, you can implement repeat MOS. If you have the right states, you can implement repeat MOS to call the right instructions, right, as a loop. So basically, in your state machine, you can have a loop that somehow controls, let's say, I'm going to make this up, but let's say this is the states for load. These are the states for add. And you're going to do repeat MOVS. When you get repeat MOVS, you get into a special mode that can repeatedly call add, load, and then add states that go back to repeat MOVS somehow and keep track of some special state to ensure that that loop executes correctly by executing add, load. I guess what else do you need? Multiply, shift. Shift you probably don't need for repeat MOVS. Okay? And that's how repeat MOVS is implemented today in machines. There's another benefit, which I'll go into a little bit. You can update the machine behavior, because this is actually a programmable machine now. Right? It's not hardwired control. Hardwired control is very hard to change. Now you actually have these micro instructions. If you could update these, perhaps you could change the behavior of a processor after it's shipped. Right? This enables ability to add new instructions without changing the processor. All you need is to send a microcode patch, right, that somehow securely gets stored in your microcode store. And if you could generate new instructions that can be expressed as existing micro instructions, you could do that, right? Or you could, I put it the way I didn't want to put it necessarily. If you could have instructions that could be implemented using the existing microcode and control structure, as well as the data path, you could do that. You could actually have the ability to fix buggy hardware implementations, right? Let's say one microcode bit was set wrongly. Well, you could send a microcode patch, just like a software patch, that gets installed on these machines, and you could fix that bit if you figure that out late after the processor is shipped. Whereas if you had hardwired control, purely hardwired control, this is very, very tough to do. You need to have the ability, some additional gates to fix that. Does that make sense? So there's another benefit to this, which is powerful. This is just like a software patch, right? You keep getting software patches from different software vendors, and you can patch your machine. And this microcode patch is like that, too. There are many examples of this. One of the earliest examples, IBM 370 model 145. You have microcode stored in main memory, and then can be updated after a reboot, which means that when the machine first starts, it takes the microcode from main memory and puts it into this special memory within the processor. So the microcode itself that's controlling the processor is still in the processor, but you have a version of the microcode in main memory that can be updated, and whenever the machine starts, it basically reads the microcode and places it into the special store. And this actually exists in IBM System Z today. These are the mainframes, the big mainframes that execute a lot of transactions, expensive mainframes. And you can read about this in this nice paper, Millicode and an IBM Z series processor from IBM designers who actually designed the millicode of that machine. They called it Millicode. But we'll get to Millicode very soon. But it's really microcode. And Burroughs 1700, as I told you, this is, again, a historical machine. I've given you the reference to this. Its microcode could be updated while the processor is running. Can you think of that? It's such a powerful abstraction that you could update the microcode while the processor is running, which is basically a user microprogrammable machine. You expose these micro instructions to the user. And you can read more about that. OK. Basically, the point is you could implement any ISA this way. And MIPS ISA is no different. A microcode implementation of MIPS is provided in this appendix. We will not cover this in class, but this is your extra credit assignment. And I'll just flash through a bunch of slides that show that this is doable. It may not be the best implementation, but this is from that book, which is available as an ebook. But this is essentially some instructions, actually maybe a good subset of the instructions that are implemented using microcode. This is the finite state machine. This is the control logic. This is the control store. So you get some inputs and you get the outputs that control the different control signals, which is very similar to what you will implement in your single cycle design. So you could perhaps use this from the book to implement your microcoded design. And then this is the state. This basically determines the next address that you use to include it, along with the opcode. So here, if you look at it, the opcode is part of the next address. So this design did not minimize the number of states you can have. And this is the microprogram control. OK, I'm done flashing these slides. OK, there's the concept of horizontal and vertical microcode, and I'll cover these briefly because you may hear this. Horizontal microcode is you have a single control store, single microcode storage. Very similar to what we've seen. And you get the control signals at the end. And it's called horizontal because it's horizontal this way. There's also vertical. I guess it depends on your viewpoint, right? What is horizontal and what is vertical? You could look at it this way and it becomes vertical. The vertical microcode is actually you have two control stores, and you have an intermediate register transfer level, that's what this RT stands for, representation. So basically you translate a micro-instruction to a register transfer level micro-instruction, which later gives you the control signals and index into another ROM. Why would you like to do this? Because there are some common operations that you do in a given state, right? So you index into this microcode, first level microcode, and the operations you need to do is PC +4, for example. And you index into the next level microcode to get the micro instruction to do that. And if you design this well, these two stores together can be smaller than a single store. And people have optimized this because this was so important, right, to keep the size of the size of this control store down. Basically, you're using a level of indirection and exploiting commonality between different states to minimize the size of all of your control store. It's fun to think about. And it's vertical because it's going this way, right? It's not going this way. OK. And you'll hear the concepts of nanocode and millicode. These are actually, you can think of these as microcode at different levels of abstraction. Nanocode is usually a level below traditional microcode. Basically, let's say you have a floating point operation, a complicated floating point module. That can be implemented. The control for that can be implemented with microcode also, specialized for that floating point unit. Millicode, it's a level above the traditional microcode. You can have ISA level subroutines that can be called by the microcontroller itself. So let's say you get a page fault in an instruction. You could go to a higher level of abstraction that actually calls the current microcontroller. Right? So you can do complicated operations and system functions this way. And if you're interested more in this, you can take a look at this. This is actually a nice paper to read when you have the time. It's not required. So in both cases, the goal is to avoid complicating the main microcontroller. I'll give you one example. This is the Nanocode. You have a microcoded floating point unit implementation. Basically, when you get a floating point operation, you have this microcode that controls this data path. And the processor can call that microcoded floating point implementation. Right? This is called Nanocode when the system itself calls it. Basically, you can think of these as function calls. Right? You get a floating point operation which invokes this microcontroller over here. Make sense? So it's really microcoded control. Each of these are microcoded control, except it's at different levels of abstraction. Right? If you look at the system itself, then you could call this nanocode. If you look at the floating point implementation itself, it's really microcoded control. Right? So these terms are not really, you'll hear these terms, but they're not really, not everybody will know and use these terms. It's really versions of microcode. OK, so I'm wrapping up. So hopefully you should know the advanced and disadvantages of multi-cycle and single-cycle microarchitectures very well by now. And microprogrammed and hardwired control as well. Any questions on any of these? Okay, and homework will help you to know these a lot more. But of course, with everything, there are advantages and limitations, or disadvantages to every single design. So what limitations do you see with the multi-cycle design? We've actually discussed this in a past lecture. If you think about the LC3B data path, is there a limitation? Can you do better? Are we actually doing the best in terms of this equation, execution time equation? No, people are shaking their heads. What is a big limitation? Are we not exploiting something that we have? Yes. And that's the hardware itself, right? You have limited concurrency when you have the state. And that state, remember, there was one state that only exercised memory. The entire data path, including the bus, is not utilized. Right? Well, that's kind of a waste, right? Basically, you're limiting the concurrency with this design. You have some hardware resources idle during different phases of the instruction processing cycle. For example, fetch logic is idle when an instruction is being decoded or executed. Most of the data path is idle when a memory access is happening. Then the question is, can we actually use the idle hardware to improve concurrency? And that's how we will get to pipelining. First of all, we want concurrency. Why? Concurrency means we can do we can reduce the cycles per instruction, right? In the same cycle, we could potentially execute different instructions. We could do more work in one cycle. We could increase the throughput of the machine. So idea is simple. When an instruction is using some resource in its processing phase, process other instructions on idle resources that are not used by that instruction. And hopefully this way you won't add too much hardware to that nice data path. I don't know if that will be true in the end. You'll also figure out firsthand when you do your pipelining lab if that's true or not. But you could process other instructions on those idle resources that are not needed. For example, when an instruction is being decoded, fetch the next instruction. When an instruction is being executed, decode another instruction. Decode the next instruction. When an instruction is accessing memory, execute the next instruction. And when an instruction is writing its result to the register file, access data memory for the next instruction. And as long as these are nicely independent, you could do all of these in the same cycle. Right? Now what you've done is, if you've done something like this, you've quadrupled the throughput of your machine. Right? You're really processing 4 instructions in a given cycle. Except they're operating on different stages of their execution phase, right? Instruction processing cycle. Powerful. Right? Okay, so that's the basic idea. More systematically, you pipeline the execution of multiple instructions. And you probably read this analogy. You have an assembly line processing of instructions. Right? We divide the instruction processing cycle into distinct stages of processing and ensure that, this is important, there are enough hardware resources to process one instruction in each stage and process a different instruction in each stage. And instructions consecutive in program order are processed in consecutive stages. And I've already given you the benefit, right? It increases instruction processing throughput, 1 over CPI. You could think of the throughput as IPC, right? Instructions per cycle. Whereas execution time is dependent on cycles per instruction. Are there downsides? Who says yes? Yes?
You could have data hazards.
That's right, yeah, I mean, we'll get to that. That's good, you read the chapter. Are there other downsides? There must be, right? Start thinking about it. Like once you pipeline the execution, you need some additional hardware, right? And we'll see what that hardware is. But I'll give you the beautiful part first. So for example, if you have the execution of 4 independent adds, and let's assume that multi-cycle add takes 4 cycles. I just made it up. If you have a multi-cycle machine without pipelining, it'll take 16 cycles to execute all those instructions. Each of them takes 4 cycles. Whereas if you have a pipeline machine, now you have 4 cycles per 4 instructions in the steady state. Steady state means that's the state where the entire pipeline is full. So in this case, if you look at this, your pipeline is not full in the first cycle, right? You fetch the first instruction. In the second cycle, your pipeline is still not full because execution and write-back stages, there's nothing there. You're filling your pipeline. In the third cycle, you're still filling your pipeline because you haven't fetched the fourth instruction. But if you look at here, this is the steady state of execution. At this point, all stages have an instruction that's being processed. Your pipeline is full. And if you keep fetching instructions, if you had more adds here, you would be in your steady state for a while. Right? And the rest of this, for example, here, your pipeline is again not full. You're basically draining your pipeline in the end. That's the end of the program. So at steady state, you improve the throughput significantly. But you got to fill your pipeline, and you got to drain it. And we'll see when that becomes an issue. If you cannot keep the pipeline full, then you won't get this high instructions per cycle. That's very fundamental again. Keeping the pipeline full is very important. We'll get to that. OK, you've probably seen the laundry analogy. Yes? No? Some of you have if you read the chapter. But basically, this is actually a nice analogy to describe pipelining. Assembly line is another one, but laundry is also nice. Let's say you're doing laundry. There are 4 steps. And if you have many different loads that are independent of each other, and when you're doing laundry, let's say you have 4 people doing laundry, or you have 4 different loads to do laundry, one thing you could do is not start the next load until you finish the first load entirely. Well, that's not very smart, right? Because once you have your, once you're done with the washer, you take the first load to the dryer, and once you're done with it, you fold it, and once you're done with it, you ask someone to put the clothes away. Actually, you probably want to ask someone to do all the steps if you want. Well, that's sometimes fun to do laundry too. But it makes no sense from a time perspective. If you do this, it makes no sense to not start the next load, not put the next load into the washer when the first load is finished with the washer. Right? You'll be there until 2 a.m. apparently if you start at 6 p.m. If you do a multi-cycle design, multi-cycle laundry processing. In this case, the load goes through sequentially dependent stages, right? You cannot start the dryer for a load before you wash that load. Let's say you're washing the colors here and whites here. Yeah, you cannot do that. So each step is sequentially dependent. But between different loads, you have no dependence, right? And different steps do not share resources. You don't dry a load using the washer. There's no sharing of resources. There's a dedicated resource, dryer, for drying. So pipelining, this is really simple, right? Start the next load while the first load is being dried. While the first load is being folded, you start the next load goes to I guess this is the dryer. It's hard to tell sometimes, huh? And you start the third load in the washer. And at the steady state, you're utilizing all the resources concurrently. And you're doing 4 loads per cycle, per time unit. And you don't need any additional resources, which means that you've increased your throughput by 4. And if you do the calculations here, I believe this is assuming that each of these steps takes 30 minutes. Then you've maximized your throughput. So instead of being done at 2 a.m., you're done at 9:30 p.m. And you can do your homework. You can do LC3B microcoding after that. So the key here is the latency per load is the same, right? But as you know, or if your dryer is the same as mine, this dryer always takes longer for some reason. Is that true? Yes? OK, that's your experience too. It's not my dryer then. And once that takes longer, it's not as beautiful anymore. Now you're not done at 9:30 p.m. You're done at 11:30 p.m. and you have less time to do your microcoding. Well, what's the point here? The dryer takes 1 hour instead of 30 minutes, and you have only one dryer, which means that you cannot put the second load into the dryer before the first load finishes, right? Which delays the processing of the second load in the dryer. So here, for example, you could actually start washing the second load here, but you have to wait until the dryer is finished with the first load, right? This is because the dryer took a long time. Well, the key insight is the slowest step actually decides your throughput, right? The throughput is really dependent on this step. Well, how can you get back to 9:30 p.m. here? Yes?
Let's go buy another dryer.
Go buy another dryer, yes. Exactly. And that's what we do. Go buy another dryer, dryer A and dryer B. And somehow it didn't get back to 9:30, but I'll let you figure out why that is. Why? Because the dryer is longer latency, right? That's why you cannot get back to 9:30 if your dryer is fundamentally slow. You really need to make the dryer faster. That's another solution. But maybe fundamentally you cannot do that. Yeah, you go buy another dryer. Now you can do the second load on the second dryer. That way you restored your throughput. You can still do 2 loads per hour using 2 dryers, right? But your latency, entire latency, is still long because that operation takes long. That's the difference between throughput and latency, right? Your throughput is still at the steady state 4 loads per cycle, right? But your latency is longer because an operation takes much longer. Make sense? That's another fundamental thing. Okay, so an ideal pipeline, well, what happened here? We wanted to increase throughput, but we added more cost, right? A dryer is expensive. A good dryer is even more expensive. So in an ideal pipeline, we would like to increase throughput with little increase in cost. In case of instruction processing, it's the hardware cost. I guess in case of dryer, it's also hardware, right? So how do you get this ideal pipeline? If you have repetition of identical operations, that enables your pipeline to be ideal. The same operations repeat on a large number of different inputs. And if you can think of the instruction processing cycle that way, right? Every fetch operations repeated on many different instructions. So you can pipeline those different instructions. Execute is also. You have repetition of independent operations. There is no dependencies between repeated operations, right? There's no dependencies between different instructions. There's no dependency here between different loads, right? That's what enables this pipeline to be relatively perfect. So in an ideal pipeline, you would like those operations to be independent. But we'll see that this may not be the case with instruction processing, right? And you would like to have these sub-operations to be uniformly partitionable. Now this is kind of a mouthful, but what does this mean? You can divide processing evenly to unit latency, or uniform latency sub-operations. That was the problem we had here. We couldn't divide processing to uniform latency sub-operations. This dryer took much longer. Here, if you can divide, you can partition your operation into uniform latency sub-operations, sub-stages, then you can get an ideal pipeline. Your stages would be balanced. And we'll see that this may not be the case again. So a fitting example is doing laundry. Actually, doing laundry, I said it's a fitting example. It's not a perfect example. But usually this is the case when you're doing laundry or automobile assembly line if you form your assembly line nicely. So I'll let you think about instruction processing cycle for a while, because we'll see that actually instruction processing cycle violates all of these. You don't necessarily have identical operations for each instruction. You don't necessarily have independent instructions. And you cannot necessarily balance the processing between different pipeline stages, because some things just take longer. So let me finish ideal pipelining, and we'll take a break and then go into even more interesting issues in pipelining. So if you look at ideal pipelining, ideally what you would like to do is this. This is the inputs that you get, that you latch. You have some combinational logic. This is a single cycle design, right? And this is the bandwidth or throughput of that single cycle design. If everything takes t picoseconds, your throughput is 1 over t. Ideally, you would like to divide this into two stages. Let's say fetch, decode, execute, and the next stage is memory, write back. And keep the throughput as 2 divided by t. And when you divide it into 3 stages, you would like the throughput to be 3 divided by t. Right? Basically, you would like to be able to divide the single cycle logic into arbitrarily small substages or stages such that your throughput is linear with the number of stages. Now, this is going to be tough. More realistic pipeline. Well, first of all, this is your non-pipeline version, right? First of all, you have a delay. Whenever you add a new stage, you're adding more delay, right? So your throughput is degrading because of that. So this is the non-pipeline version. If you look at if you add some more realism into this, you have t picoseconds, but you also have some s picoseconds, which is the latch delay. It doesn't come for free. Now, there are some cases where you can actually hide that delay, but you cannot arbitrarily hide that delay. So your throughput is actually 1 divided by t plus s, where s is the latch delay. And when you start pipelining, now you're adding, maybe you're dividing t by k. Let's say you have k stages. You're dividing t by k because hopefully you're balancing your pipelines. But you keep adding this latch delay. You cannot overcome that. It's very hard to hide that latch delay. Which means that your maximum bandwidth, let's assume you can divide up, your stage is 1 gate delay long. Your maximum bandwidth is really dictated by that latch delay, S. And that may not be very high. That's why you cannot pipeline arbitrarily, right? Well, this is one of the reasons why you cannot pipeline. This is the latency reason, right? Your latency keeps increasing, actually. If you look at cost, your cost is actually the gate cost in this combinational logic plus the latch cost. And as you keep adding pipeline stages, you keep adding latches, right? Maybe you're perfectly partitioning these G gates that you start with, which is a tough problem. But you're always adding these latches. So that's a big cost that comes with pipelining. So the world is not perfect. That's why people don't pipeline arbitrarily. This is one of the reasons. We'll see many other reasons, actually. Make sense? And think about the power. You could do this power analysis also. People have looked at what is the ideal number of pipeline stages that you have in a processor. Well, it's definitely not 1,000. But it's definitely not 1 also. So it's somewhere in between. And that does depend on what are these values. And this is a very simplistic equation for cost. OK, I think let's take a 5-minute break. And we'll start delving into very interesting issues in pipelining. Let's be back at 1:35. OK, let's start with the instruction processing pipeline now. This is the instruction processing cycle that you've seen and gotten to love so far, right? And fetch, decode, evaluate address, fetch operands, execute, store result. You can see it in many forms. And we're going to pipeline the single cycle microarchitecture, which is basically a preview of your next lab. So you could use this lecture to start your next lab. And remember, your next lab is actually available in the previous year's website. So if you're so ahead that you're done with your second lab, you could do that. I'm just joking. Don't try to do that necessarily. Do the extra credit. OK, remember this is the single cycle microarchitecture that you're going to build in this lab. And this is what it looks like. So let's say we would like to divide this into stages. And I'm going to abstract some things, because I don't want to deal with every single signal here. But this is one way of dividing this single cycle microarchitecture into pipeline stages. You have fetch, decode, execute, memory access, and write back. And this is the amount of time the critical path takes in each stage. 200 picoseconds, 100 picoseconds, 200, 200, 100. Obviously, it's not balanced to begin with, right? Is this the correct partitioning? Why not have 4 or 6 stages? Why not have different boundaries? Why not have, I don't know, maybe 1, 2, maybe make your clock cycle 100 picoseconds and have even more stages, right? You'll add 3 more stages that way. That's the first question you ask in a pipeline design, right? what is the correct partitioning? And that's where those microarchitecture design principles become important, right? You got to balance the pipeline. And we'll see some issues related to this. Okay, so what else do you need to do this partitioning? These are questions I will not necessarily answer, but you can think of what it goes to this. You'd like to ideally have a balanced pipeline. But you would also need some other things. You would like to be able to have the ability to provide write back while somebody else is reading from the register file. How do you do that? Right? Before, there was only a single operation, either reading or writing to the register file. Well, there's something that needs to do RF write. And how do you handle this thing? I'll tell you ignore for now, but there is the target address that's generated here, and that goes through multiple stages, right? Similarly, this register write goes through multiple stages to write back. So how do you handle this? How do you ensure that the pipeline works correctly when somebody is changing the control flow, when you're fetching instructions here? These are all fundamental issues that we will cover. But let's take a look at the throughput first. This is how we've divided the stages. So this is, let's say we have 3 independent load instructions. This is the multi-cycle execution. And you've already figured out that this is not a good design. It takes too long. 800 picoseconds to execute each instruction. Now we pipelined this machine into 5 stages. We would like to see our speed up to be 5, right? 5x. We'd like to finish an instruction every 160 picoseconds. Ideally, that's an ideal pipeline. But if you look at this, with the way we've divided, this is what our pipeline looks like. This is the pipeline operation of these 3 loads. Each stage takes 200 picoseconds, even though it may not need it, because the critical path may be much shorter. But you have to design the pipeline such that every stage operates in the same clock cycle. So this is the first instruction. While you're doing a register read for the first instruction, you're fetching the next instruction. While you're doing an ALU operation, address generation for the first load, you're doing a register read and decoding for the second instruction. And you're fetching the third instruction. And everything takes 200 picoseconds. And if you look at this, the speed up is really 4 and not 5. You don't complete an instruction every 160 picoseconds, which is what you would ideally want. You complete an instruction every 200 picoseconds. Why we couldn't divide the processing into 160 picoseconds? Right? The stages are not balanced and not perfect. And you will have this issue with pipelining. So how do you enable this pipeline processing? Let's see. You need something to latch the results of the instruction that finishes in the first cycle. Instruction fetch results should be latched. And every stage should communicate with the next stage with a latch. Right? So we're going to add pipeline latches. This is the IFID, instruction fetch, the latch between instruction fetch and instruction decode, between instruction decode and execute, ... And what do the latches store? They store both data and control. And for example, here we have PC plus 4, program counter plus 4 stored at the end of this addition. And we somehow propagate that PC plus 4 because we do not know until the branch executes whether the next PC should be PC plus 4 or the target of the branch. Right? So you need to propagate this PC plus 4, even though you may do the addition here. And this is where you generate the target address, actually. And this is not complete, by the way. You're going to design a complete version of this. So this doesn't give you the full thing. So no resources used by more than one stage here. So let's take a look at some examples. I mean, you can, once you design it, you will see what you need to propagate and what you don't need to propagate. But you would like to propagate to later stages those things that are needed by the later stages, obviously, right? Which means that your pipeline latches initially are big, and they become smaller as you go down. Is that always the case? Maybe you generate more information at some stage, right? And then you need to latch it. So it's not always the case. But usually, you have more information in the beginning. But we'll take a look at it in the control, when we look at the control. Actually, you have less information in the instruction register, right? You fetch the instruction register. And that could be small. And then after you generate the control signals, that becomes a big latch. Okay, but we'll get to that. Let's take a look at the operation of a load word. Basically, you're fetching this load. It's accessing instruction memory, and it's being decoded. It reads the register file, and it uses this resource. And in its execution, it's utilizing some resource, this adder. And this adder is really the branch target address adder, which is not needed for load. It accesses memory, and then it writes back its result to the register file. And if you look at this, you need these signals to be able to do write back. So what we had here is you need to propagate the destination register ID, which becomes available after the decode stage, all the way to these latches, and write back result appears here. That's why you need the destination register ID, right? And you also need a control signal that says I should write back here. So all of the control signals that control this resource that happens to sit here physically come from the write back stage. Right? The destination register ID, the control signal that says you should write the data, and also the data that you're going to write. Now what happens when you have something that's reading the same register? Load is writing to R3, and an add instruction is needing that R3. Well, somehow you need to handle that case, right? And we'll see. That's called a dependence or dependency between instructions. But here, one other thing is all instruction classes must follow the same path and timing through the pipeline stages, right? Does this have any performance impact, you think? Yes. Many of you are nodding your heads. Why? Yes?
Because every instruction has to take up all of the stages no matter what.
That's right, exactly. It may not need a stage, but it has to go through that stage, right? Maybe an instruction doesn't write back a result, right? A branch instruction, at least the way we designed the stage, it doesn't write back anything. It's resolved here. Right? Maybe an instruction doesn't need memory, and there are many such instructions, right? In fact, in general, there have been many studies, but a good rule of thumb is 40 to 50% of instructions are memory instructions. This does depend on how many registers you have also in your ISA. But 40 to 50% of the instructions are memory instructions, which means that every single instruction is going through this memory stage, even though only half or fewer instructions need the memory stage. So there's a performance impact. But if you try to ensure that those instructions actually don't go through the pipeline, then the abstraction becomes ugly, right? Now you have to have a special case where those instructions skip this pipeline stage. And you can imagine the bad things that you need to do to the design to make that work. But you're the architect. You can actually make that work too. But that comes at a cost. It's not beautiful. It's not flowing anymore. Some instruction takes a special path. But in an existing machine, actually, there are those special paths. Floating point, when you get to the execution units, because floating point units take much longer than an integer adder, instructions can go through different pipelines. And now you need to ensure that the instructions don't collide at some point when they're writing to the register file. And we will see that when we cover out-of-order execution or multi-cycle operations. So think ahead a little bit. This is nice if your ALU takes 1 cycle, right? Well, what if your ALU takes 50 cycles? You have a divide. Do you want to limit your concurrency, or can you actually do multiple operations? Or multiple operations, can you actually start multiple operations the pipeline way? Okay. So if you have 3 load instructions, well, I guess it's a sub-instruction. I've changed the code for you. You have an instruction that's loading, and you have a subtract instruction that's independent of the load. These flow nicely, right? And I'll let you go through this. You got the concept, right? And you could, we're going to visualize this in different ways. You could look at it from an operation view while instruction 0 is being fetched. While instruction 0 is being decoded, the next instruction is fetched. And this is what I mentioned with the steady state of the pipeline. While at this steady state, once the pipeline is full at time t4, all of these 5 instructions are being processed in some stage. Right? So you get the full throughput of your pipeline. So you would like to keep the pipeline full. I'll give you one other picture. You can think of it from a resource view also. This is the operation view. Operations get executed in time at different stages. But you could think of it from a different stage view, instruction fetch stage. At time t0, you have I0. Instruction decode stage at time t1, you get I0. So ideally, you would like to maximize your resource utilization. At different points in time, the fetch stage should have different instructions. The decode stage 2, execute stages 2, memory stage 2, write back stage 2. That's how you can make best of use of your pipeline. But we're going to see that that's not always the case because of dependencies between instructions. So what about control? Let's take a look at the control. Basically, control points do not change, right? Your data path is really the same. You're just broken up into pieces. You still need to control your ALU somehow. You still need a register write signal. The points are the same. But where those control signals come from is not the same anymore. In a single cycle, you generate the control signals in that cycle. In a pipeline machine, well, the control signals need to be determined at different stages of the pipeline, potentially, right? So for given instructions, you have the same control signals as single cycle, but control signals required at different cycles, depending on the stage. What you can do is you can decode once using the same logic as single cycle. You can basically generate the control signals for an instruction using the same logic that you used for the single cycle design, or that you're going to use for the single cycle design. And buffer the control signals until you need them. Basically, the idea is, well, maybe I have it. Oh, there you go. Once you have the instruction, you generate the control signals. And some of these control signals will be needed in the execute stage. Some of those control signals will be needed in the memory stage. Some of those control signals will be needed in the write-back stage. Right. Obviously, whether or not an instruction writes to a register, that particular control signal that controls the register writing operation is not needed here because in execute and mem stages, there's no write-back that's happening. We've divided our pipeline that way, which means that you need to propagate that signal to the next stage. So that's what it looks like. And this is what I mentioned earlier. This pipeline stage latch is probably bigger, right? Because you generate all of the control signals beforehand. And it becomes smaller because you consume some of the control signals and you don't need them anymore. Okay? Or another alternative in designing control for a pipeline machine is you don't generate all of the control signals in this decode stage, but you generate as you need them. Right? For example, you can carry the relevant instruction word or field down the pipeline and decode locally within each stage. And it's still the same, almost the same logic to do the decoding if it's hardwired. Right? I guess what is the advantage and disadvantage of each, or which one is better? One option, you generate all your control signals in the decode stage and then propagate them and consume them as you need them. The second option, you generate as you need your control signals. For example, the control signal that's needed, the write-back control signal, is not generated here, but it's generated in the write-back stage. And how can you do that? By basically checking the opcode in the write-back stage, right? And if it's an opcode that writes to a register, you generate the control signal there. I guess what is the advantage of the first one versus the second one? This goes back to something we've discussed. When do you generate your control signals? Only one decoder, the first one, right? Yes, that's true. Although in the other case, you have distributed decoder, right? You're basically distributing your decoding. Yes?
You don't have to propagate through the instruction to capture that for each decoding stage.
So in the first case? Or?
Oh, sorry, no.
In the second-
If you're going to distribute it, you need to remember what your instruction was.
That's right.
To actually properly decode it each time.
That's right, yeah. If you're doing it this way, you need to propagate your instruction. But if you're doing it this way, now you need to propagate your control signals, which may be bigger than your instruction. Yes?
If you have exceptional conditions that can occur in said execute state. Like if your ISA specifies that if an overflow occurs, no write back occurs, and you've already generated the control signal to the write back, then you have to have some funky logic to prevent the write back. Whereas if you had generated the control signals in the write back stage.
I see. You still need to do the same thing though, right? You still need to ensure that
It's not that big a difference, but it means you don't have to. It means you generate the control signals and they're right. You don't modify the control signals halfway down the pipeline.
That's right. Yeah, you basically need an additional gate, but it looks like it's going to look like the same. Basically, you either generated the write back control signal beforehand and gated it with the exception condition over here, or you just have the exception condition generated and you ensure that that write back signal is generated as 0 here. So in a sense, it's very similar. But I think you may have one more thing, which is you wasted a lot of effort perhaps here, even though you're going to get an exception, right? But that's an exceptional condition, so let's not optimize for that. Okay. There's another thing, right? What if your generation of control signals takes a while? Yeah.
In the current design, the code is a pipeline stage all by itself.
That's right.
Since it is designed this way, it's very likely that it is huge by itself already, since it's consuming one whole pipeline stage. Now, if you replicate its functions across every single other pipeline stages, then you are potentially wasting a lot of transistors repeating unnecessary tasks.
That could be true, yeah. That depends on, I guess, what you repeat in each stage. That's potentially true. You can have, I think the trade-off you're getting at is, do you have more storage in your pipeline latches, or do you have more hardwired logic? And that's not clear also in the design. But there's one more thing, which is, if you generate your control signals here, they're now available, right? You can use a full clock cycle, later clock cycle, to just do data path processing. Whereas if you generate your control signals on demand in the write back stage, for example, maybe that's not the best example, but let's say in the write back stage, you generate your control signal, and that control signal controls the register file. Maybe you lengthen your clock cycle, right? If the generation of that control signal takes a long time. So the same principle applies here. You don't want to generate the control signal in the same stage that it's going to control the data path elements. You would like to generate it beforehand. In this design, if you generate everything early, well, maybe you avoided the problem of control signals getting in the way of data path processing or extending the clock cycle. But again, there's a caveat, right? It may take very long to generate your control signals because you're trying to generate all of them at the same time. So that's where this becomes art also, yes.
Can you have distributed decoding but have the control signal generated right before?
Exactly. So that's the other option, right? So as long as you can generate your control signals the cycle before you need them, you can avoid that problem. So there are many ways of designing this control. But one of the downsides of actually generating all of the control signals here is your pipeline registers may become unbalanced. You could have a huge register at the end of decode stage. And you will see that in the LC3B design. In the pipelined LC3B design, you can actually calculate the size of those registers because we've specified everything for you. OK, that's fun to think about. But never forget the fundamental principle. If your control takes too long, don't generate that control signal in the same cycle you need it. Generate it beforehand. OK, so these are the pipeline control signals for the design that you're going to do. And we've opted for generating at least most of the control signals in the decode stage. That's what this control is. You generate the control signals for different stages that come later. And then you somehow generate some other control signals within other stages also. But you'll figure this out when you do your lab. So for example, this is the control signal for the register write that I described earlier. That control signal gets propagated and eventually controls the register file from the write back stage. OK, So we've discussed the ideal pipeline, right? Ideal pipeline, remember, I'll flash these again. You want identical operations, the same operation repeated on a large number of different inputs. Fetch operation repeated on a large number of instructions. A repetition of independent operations, there are no dependencies between these instructions. And you want uniformly partitionable sub-operations. You want these stages to be the same, and you would like them to be partitioned to the same length, to the same cycle time, or to the same critical path. And we've seen fitting examples for this. I guess, what about the instruction processing cycle? Does it satisfy all of these? Now you've seen that we cannot uniformly partition, right? In that pipeline, some stages took 100 picoseconds. And it's a hard problem to actually balance all of these pipeline stages. What about the first two? Well, you've already seen that identical operations, not every operation is repeated on the same instruction. Some instructions do not need the memory stage. Right? Make sense? So an instruction pipeline violates these two. It does violate the third one too. Operations are not independent of each other, right? You can have an add instruction that's dependent on the previous load instruction. So how do you handle that? Well, I guess I've covered this, and this is for your benefit mainly. But you could think of this, I'll just cover a little bit. Different instructions do not need all stages. You could think of this as external fragmentation, right? You have some pipeline stages, but those stages are idle for some instructions. Right? You basically fragmented your processing. And you can have internal fragmentation also. Different pipeline stages now have different critical paths. You've set your clock cycle to the longest critical path, longest stage, but some pipeline stages do not use that critical path, which means that internally in that clock cycle you have some fragmentation across different pipeline stages. Right? Not all pipeline stages are using the entire clock cycle. And independent operations, instructions are not independent of each other, at least. You need to somehow detect and resolve inter-instruction dependencies. Actually, not all instructions are independent of each other, right? And you need to ensure that the pipeline operates correctly in the presence of these dependencies, which means that the pipeline is not always moving. Right? If an instruction needs the result of a later instruction, and that later result cannot be produced quickly, that this instruction better wait. Right? Now that waiting is called stalling. That pipeline stalls. This instruction and any instruction that comes later it cannot move in the pipeline until the value for that instruction becomes ready. And this is going to reduce something here. What could it reduce here in this equation? Number of instructions, cycles per instruction, cycle time. Cycles per instruction, right? Oh, increase, yes, that's right. That's right. Increase cycles per instruction. Because the pipeline is stalling, you're not processing the same number, more instructions in a cycle. You're basically doing nothing for a while until instructions become available. Okay, so these are some of the issues in pipeline design, actually. There are three key issues. First is, how do you balance work in different pipeline stages? How many stages do you have, and what is done in each stage? We're not going to cover this in detail, but this is an important issue also. Second, which we're going to cover in detail, is how do you keep the pipeline correct, moving, and full in the presence of events that actually disrupt this pipeline flow? And what are those events that disrupt the pipeline flow? I've told you about dependencies, handling dependencies. We're going to look at data dependencies and control dependencies. Although you will see that control dependency is a form of data dependence, right? Anybody guess why?
Sees data. So.
Exactly. You could think of the program counter as data produced by an instruction, right? It's a special form of data dependence because the next instruction is dependent on that data piece. So we're going to handle that a little bit specially. Resource contention is another thing that can disrupt the pipeline flow. If both stages, if two stages need the same resource, and you have only one of that resource, somehow you need to arbitrate. And register file could be one of those, right? And handling long latency multi-cycle operations. And if an instruction is multiple cycles, again, that could disrupt the flow, right? Because it may remain in the same stage for multiple cycles. Memory operation, for example, right? We have nice memory. What if the memory takes 100 cycles? How do you keep the pipeline moving for those 100 cycles? We're going to assume that the memory has actually one cycle here. But later in the course, we're going to try to design techniques that minimize that, that ensure that the memory is actually one cycle. And you already know what that technique is, right? Caching. We try to do caching such that memory is most of the time one cycle, even though the huge memory is hundreds of cycles, right? So we're going to assume for now that memory is one cycle, but that's not the case in real life. Okay, and the third thing is handling exceptions and interrupts. It's good that some of you are thinking about this already. How do you handle exceptional conditions? This also disrupts the pipeline flow. And interrupts. Interrupts are external. And we'll also cover improving pipeline throughput. How do we minimize these stalls? So let's start with stalls, I think. What are the causes of these pipeline stalls? And stall means the pipeline doesn't move, or part of the pipeline doesn't move. Resource contention is one, dependencies is other, and long latency operations is the third one. What is a dependency? And you read this in your book. But it's also, well, I'll actually use the term dependence and dependency interchangeably. It has the same meaning. Your book calls it a hazard. I think this is less desirable. The fundamental thing is there's a dependence between one instruction and the other. It becomes a hazard if you do not handle it well. Right? Hazard sounds dangerous, right? If you do not do something about it, it can become hazardous. But it's really that dependency that leads to that hazardous condition. And we're going to do something about it to make sure the pipeline works correctly. Dependencies dictate ordering requirements between instructions, right? There are two types of it, data dependence and control dependence. And resource contention is sometimes called resource dependence also, and you'll see it in some of the books. But again, this is not fundamental to the program semantics, right? It's not dictated by program semantics. It's really hardware resource that's being used by multiple different instructions at the same time, or that's needed by multiple instructions. So we'll treat this separately. Okay, let's take a look at that first. How do you handle resource contention? This happens when instructions in two pipeline stages need the same resource. Can anybody think of in the pipeline that we discussed, what are some of these resources?
In your arithmetic operations, you have an add and subtract with the same register. They use the same register.
But they do not need the same resource at the same time, right? You're thinking of the ALU, I think. So there can be only one of those operations in the execute stage, right? So they do not need the same resource at the same time. At least that resource. They do need some other resource. Well, actually, is that true? No, not adds. So remember, fetch, decode, execute, memory, write back. I'm thinking of, do you have two instructions at different stages that need the same resource? That add and subtract need the same ALU, that's absolutely true, but they need it in different cycles. So there's no resource contention. Yes?
How about increasing the program counter and adding or something?
Oh, if you use the ALU for that, yes. But we're going to provide a separate resource, separate addition. You're right. That depends on how much resource, what resource you provide. If you have only a single adder in your machine, then every instruction needs the same resource, right? But we're going to treat the program counter separately and have a special adder here. That's not the greatest adder, but you can imagine PC plus 4. It's the same as your single cycle design that you'll do. Yes?
What about reading and writing from memory?
That's right, reading and writing from memory. You mean loads and stores or something else?
Or I guess don't you have to read from memory the instruction as
That's
well,
right.
and maybe you want to write on the cycle?
Yes, maybe you want to read at the same time, right? Maybe you have a load here, and you also need to fetch the next instruction, right? And this is the first fundamental resource, memory. Memory is needed in both stages of the pipeline. How do you fix that problem? Well, you could be writing, reading. Well, okay. What else? I'll handle the other case, and then we'll get to memory, actually. Memory is somewhere over there on the slide. Apparently, it's not the next. My prediction did not work correctly. Yes?
Is the register file?
Exactly. Register file, right? An instruction may be writing to its destination register, whereas another instruction may need maybe not even the same register, right? But this resource is still contended for. You have this register file. One instruction needs to write to it. Another instruction needs to read from it. If you have a single port in that register file, well, too bad. You're going to ensure one of the instructions finish. And which one? Which one do you prioritize? Let's say you have only one port in your register file. Write back, right? Yes, you prioritize this one so that the pipeline keeps moving, right? If you prioritize this instruction that needs to read the register file, then this instruction is now blocking the pipeline. So always prioritizing the older instruction in a pipeline like this enables pipeline to move. Okay, so these are two resources. So how do you eliminate this issue? Well, you add another port to the register file, right? Basically, that's the first solution. Eliminate the cause of the contention. You can duplicate the resource or increase its throughput. That's what we've done with adding a port, yes.
So if you just add a reading port, couldn't that mess with the correctness of the program? Because like say you were updating the same register.
Yes.
And what happens if you were supposed to write back to it first before reading from it?
So that goes into the dependencies, right? Basically, you're writing to register 2 here, and somebody needs register 2. Somebody's reading register 2. How do you ensure that this gets the correct value? So you need logic to detect this. Yeah. And you could have this logic within the register file as part of the control logic, or you could have it outside the register file. And we'll cover these dependencies a lot. For now, and for the design you're going to implement, we're going to assume that this write completes in the first half of the clock cycle, and the read can capture its value in the second half. May not be the best assumption, but it's a nice assumption, right? If you assume that this write completes in the first half and the read can happen in the second half without it lengthening the clock cycle, that's great. That way you avoided that check. But that's what we will assume for now. Okay. For example, use separate instruction and data memories, right? That's how you solve the memory access problem. If you have separate memories for instruction and data, now you don't have this resource dependence. Or you can use multiple ports for memory structures. Right? And when we cover memory, we will see that instruction and data caches are actually physically in different parts because of this reason, instruction cache and data cache. You have separate caches. Okay, solution 2, well, you can do what I said earlier, right? You can detect the resource contention and stall one of the contending stages. And I think you know the answer to this now. And I think you know the answer to this too, hopefully. Single read and write port to the register file. Well, you'd better make this instruction move. Okay, data dependencies. There are actually 3 types of data dependencies. One of them is real. The others are fake. But fake ones actually will get in the way also, as we will see later. Flow dependence, this is true data dependence. It's also called a read after write dependence. Basically, an instruction, a later instruction needs a value produced by a previous instruction. let's say you have this add instruction that's writing to register 1. These are the inputs. And you have another multiply instruction that requires register 1. This is a flow dependence, and it does something. This is a true dependence. This is the only true dependence, actually. Your program will not execute correctly if you do not obey this dependence. Nice. But there's also other dependencies, output dependence. Why is this called read after write? You have a read to the same location after a write to the same location. That's also, you will see the term read after write dependence. Now, output dependence is the case where you have an add instruction that's writing to register 1. And later you have, let's say, a multiply instruction again that's also writing to register 1. This is also called a write after write dependence. Now you need to handle this also some way. You don't want this to happen before this, right? Yes?
Why would a compiler ever generate control system like that?
Oh, code like this? Well, that's why I did ... Maybe someone uses R1, and then...
Then it would be in the first case, right?
Yeah, but this is still a dependence between these instructions, right?
I thought it's better to break it down to the smallest blocks of dependencies where the second case should be counted as like the first 2 lines are one dependency, which falls into the first category.
Well, the compiler can still generate this also, and you still need to handle it correctly. But I'm defining the dependence right now. I think you're thinking of what happens in hardware. You will see the importance of this later on. Yes?
And like using it as a global flag for some other concurrent process could be an example of using that. Like you enable the flag like a log, you do something, and then you write it again without even reading it.
That's a good point, actually. Yeah. Maybe you don't do it through registers, but you do it through memory. But you could actually enable this and expect someone else to read it somehow. That may not be the best way of programming, but a lot of high-performance parallel programmers actually do that kind of programming. Anyway, so this is, ignore right now, this is the definition of dependence itself. This instruction has these 2 instructions have output dependencies, regardless of whatever instructions are in between. When you see this, these have an output dependence. Anti-dependence is you have a write after read dependence. So you have add here. That's writing to R1. And you have a multiply. Well, I guess this one, right? You have add actually reading from R1, and you have multiply writing to R1. You've got to make sure that this multiply doesn't happen before the add, right? Otherwise, add would get the incorrect value. Now, in a pipeline machine, for all of them, we need to ensure semantics of the program are correct, or in any machine, right? If you look at the semantics of the program, this add should not get the value written by R1 here. This multiply, the latest value after executing the sequence of instructions, the latest value of R1 should be the value produced by multiply. And here, multiply should get the value produced by add. These semantics need to be maintained in any machine you design. And flow dependencies are the true dependence here. These 2 other dependencies, anti and output dependencies, why do they exist? Because you have limited number of registers, right? And this will become important when we cover out-of-order execution. You don't really need to have the same R1 here, right? These are producing different values. If you had enough registers in your ISA, this could have been R1000. Because there's no relationship between these 2 values. Here, there is a big relationship. This multiply needs the value that's produced by this add. Here, there's no relationship. It's just a storage for that particular, for 2 different values. Right? So it's really dependence on a name and not value. Right? The names of these registers that happen to store 2 different values seem to be, happen to be the same. And keep this in mind. We'll see later what we can do about them. We're going to get rid of this dependence when we try to execute these instructions concurrently. Okay, so I'll leave you with this slide. I've defined the dependence, but how do we handle these data dependencies is where we will start next. It turns out anti and output dependencies are easier to handle in a pipeline machine because we're going to write results at the very end. But flow dependencies are more interesting. And I guess you can read, you could do your readings to figure out what are different ways. Although your readings will not cover all of the ways. Let's see. Oh, I'll leave you with this maybe. Flow dependencies are more interesting, and there are 5 fundamental ways of handling flow dependencies. You could argue that this is 4. But think about those 5 different ways. And they're all interesting, they're all different. Your books will cover only 2 or so, or maybe 3. Okay? I'll see you in the next lecture.